So this is my MATLAB simulation of the two-wheel balancing robot. This has been completed within Simulink using the simscape multi-body extension. This demonstrates the PID controller and the mechanical system. This is comprised of two parts: the chassis and the cart, the same model that could be used in the cart and pendulum problem. So here I've clicked into the cart and you can see I've used multi-body body masses for each wheel and extra masses for each motor. These are all connected using rigid body transforms, keeping the whole system rigid. I've used the same multi-body body masses to describe the chassis with plates for each layer of the robot and pillars. I've added a small force, a step force, just to knock the system initially. This means that it becomes unstable. If without the external force, the system would stay at its balance point throughout the simulation, the control system would never come into play. So going back to the PID controller, we can see that the chassis is connected to the system using a free spinning revolute joint. This allows the chassis to spin around the cart as it would in reality. The output, the tilt angle of this revolute joint feeds the PID controller and represents the IMU. The cart is represented by a prismatic joint that allows it to translate. So this is the simulation of the single PID controller. You can see the multi-body simulated it, how it appears in its first prototype. Once we press play, we'll see the robot react to that initial force and balance itself. You can see vibrations in this control system, and that's due to the motor dead zones that we expect to see with our current specification motors. This means that they have a limit to how finely they can react to angle disturbances. Also, we can see that it moves away from its initial position. Looking back at the simulation diagram, I'm now going to connect the positional controller. This is a cascaded PID controller that uses the output from the prismatic joint of position. In real life, this would be measured using an integrated encoder velocity reading. This feeds directly into the cascaded PID controller that has the same motor dead zone constraints as the first controller. This is subtracted from the output to encourage the robot to return to its initial position. In this simulation, we'll see the balance system has priority, but the positional controller eventually causes the robot to return to its initial position. Again, some vibrations are expected, and we can look on the scope and see these vibrations throughout the simulation. I believe all of these are within 1 degree, which is within an acceptable range for this project. And we can also look at the scope for the position. You can see that initially, as it reacts to the force, it moves away from the 0 position and then returns back. But this converges much slower than the initial controller.